Hello everybody and welcome to another video on my channel. Today we will be talking about the very introduction to kinematics. Now, if any of you didn't know, this is the second video in my new physics channel. I originally started off as a maths channel, then I also just recently created a physics channel. So basically what this is almost like a spin-off. I'll still be continuing my math videos, of course, and I'll leave a link to that in the description. But so if you find any of those videos or any of these videos helpful, entertaining, anything of the sorts, please make sure to like, subscribe, and hit that notification button for more videos just like this. So let's move on to the actual topic. So in kinematics, we discuss how objects move. We describe their velocity, their position, their acceleration, all of that. And normally what we're working in is something called constant acceleration. So an example of that would be the following. Let's say we have a block over here and it's falling down over here in the subject of Earth's gravity. Now, it will have a constant gravitational acceleration of g, or about 10 meters per second squared. Normally, people will say it's 9.8 meters per second squared, but for most of the calculations in this video, I'll be using 10 meters per second squared. Unless I specifically say let's use 9.8 meters per second squared, 10 meters per second squared will pretty much be the norm in these videos. Now, constant, of course, means that it doesn't change. Basically, as long as you are somewhere near Earth's surface, which is pretty much going to be for all our problems until we discuss Newton's law of gravitation later, all g is going to remain effectively constant. So we can work under that frame of reference. Basically, the reason g is constant is that the Newton's law of gravitation, which is over here, I'll write it down quickly. What it is F is equal to the gravitational constant g, the big mass times the small mass, divided by r squared. Now r is the distance from the Earth's surface. Now Newton's second law states that what it is the mass times acceleration. F is equal to ma is the Newton's second law, and under constant acceleration, mg is equal to gravitational times mass times the small mass over r squared. Now, what can happen over here is we can cancel out the m's, and we get g is equal to gm divided by r squared, which is essentially a constant. Let me write it somewhere else and in a different color to show you the end results. G is equal to g, the big G, times mass divided by r squared, where r is the distance. So the gravitational constant and the mass of the Earth are both constant, but r is not technically constant. But since the radius of the Earth is something like 6 times 10 to the power of 6, as long as nothing goes so big that it's relative to the distance of the Earth, gravitational acceleration will be about constant. So that's one example where gravity is involved, called there is a constant acceleration. So that's pretty much why g is a constant acceleration. Now let's move on to a few other examples. Now these will pretty much also all involve gravity, but in slightly different ways. One of these slightly different ways is, let's say we have a surface over here. Then let's say that over here we have a projectile and we launch it, so like this. Then we have this block in mid-air and it's going down. this is projectile motion. And since normally what happens is at a certain angle to the surface, let's say theta, there is pretty much always a velocity going up. So basically, let me draw it a bit bigger. There will always be an initial velocity with some forward and some upward momentum of v0. We can split v0 into its horizontal and vertical components, and the vertical component will change because of gravitational acceleration, but there's low acceleration, and no, we are not counting air resistance in any of these problems unless specifically told to. We will not be using air resistance at all. Basically, what the horizontal is it will practically not change. So that's another example of constant acceleration using gravity. And also zero acceleration is also constant acceleration. Now, one final thing before I get onto a few formulas. The first thing that we need to do, or the final thing that we need to do, is we need to say the difference between displacement and distance. Now, displacement and distance are two very different things which serve completely different roles. The best example that I can think of is if we have a circle, then what we can do is, let's say we have 2 points, one over here and one halfway across the circle. Say we have a radius of the circle equal to r. So the radius is equal to r. Now, technically, the distance is going to be equal to the half of the circumference, so half of 2 pi r, or simply pi r. But the displacement is going to be the shortest line between the two, so straight across the center. So it'll actually be the diameter, where we have d, or just 2 times r. If you notice, the distance is actually greater than the displacement, and that will always be true unless the distance is also a straight line from the start to the finish. So that's another fact that we can write down. Always displacement always less than or equal to distance. So that's another quick formula. Another thing that we could do with this displacement over here is, let's say that we did a track all the way around the circle. So here, then all the way around the circle. Now the distance would be 2 pi r, but the displacement would be 0, since the shortest path from start to finish is just staying at that same point. Displacement does not depend on the path taken, but distance does. So now we clarified the difference between displacement and distance. We can go on to writing the final few formulas that we're going to use in this video. So I'm going to write them on the left hand side over here. So the first of these formulas is that the average velocity is equal to the displacement, or sometimes denoted delta x, divided by the time. Keep in mind that velocity also has a direction, just like displacement. In other words, they are vector quantities. In my next two videos, most likely I will be reviewing trigonometry and vectors. So don't worry about it if you don't completely understand it. Now the next thing is that the average acceleration is equal to delta v divided by t, or the change in velocity divided by time. Just like velocity, acceleration is also a vector. Now keep in mind, these formulas can also be applied in reverse. where we can have displacement equal to velocity times time. Now another one is speed, or sometimes also written v, so we'll write v, but I'll write v in a different color to show that's equal to speed, is equal to the distance, or just x, divided by time. Now with v, it's just a scalar, basically meaning it has no direction, it's just a quantity. And that can never be negative, since distance can never be negative and time can never be negative. But displacement can be negative if we attach a coordinate system to it. But we'll talk about more of that on future videos. But for now, thank you so much, see you in the next one, and bye-bye.